Cisco Certified Network Associate Day 49. Welcome back everyone, I'm Imran, your trainer for this entire series. Today we are doing EIGRP Introduction, which is also with OSPF. EIGRP is, these two topics are one of our most sought after topics ever, right? From the time we started the series, people have requested for EIGRP and OSPF. And OSPF we did in the last few videos. Today we start EIGRP. So without wasting much time, let's get straight into today's class. Before we go ahead, today's video is sponsored by Skillshare, an online learning community for creators with more than 25,000 classes in design, technology, business, and more. Whether you want to fuel your creativity, curiosity, or even your career, Skillshare is the perfect place to keep you learning and thriving in 2019. If you ever wanted to make money in the app market, then try this course today, where you can learn how to design, develop, and sell your app on the App Store. He will take you from being an absolute beginner to making you a master in app development. Try it today. Join more than 7 million creators learning with Skillshare. The first 500 of my subscribers to use the link given in the description below will get 2 months free premium trial. So don't waste time, do that right away. So what is ahead for us today? Today we would go, so we finished 2.4, so we will go from 2.4 to 2.6. We have not done 2.5, we'll come back to 2.5 later, but we would be doing 2.6 today. So that's configure, verify, troubleshoot EIGRP for IP version 4, excluding authentication, filtering, manual summarization, redistribution stuff. So this is configure, verify, and troubleshoot topics, but in today's video we would only be doing introduction. So we will introduce you to concepts of EIGRP, and then in the next video and the video after that we will look at troubleshooting and configuration, right? So before we go ahead, I want you to take a moment, right? We did about 4 or 5 videos of OSPF. So I want you to think, when we did RIP many moons ago, we learned that there was loop, right? There was a way, it was creating loops. There were possibility of loop creations, and we looked at few loop prevention techniques. What are those techniques in OSPF? How do you prevent loop in OSPF? Do we use route poison? And what about split horizon? Do we use split horizon in OSPF? So this is for you to find out. Use Google or read other resources, but find the answer for this question, because if you try doing some research for yourself, you're going to remember that. So I want you to remember, I want you to research, I want you to understand, and once you find an answer, comment in the comment section below, and let's see how many of you all find the answer and how many of you all comment. So what is EIGRP? EIGRP is a hybrid routing protocol. Now, why do we call hybrid? Because it takes some good features from distance vector routing protocol like RIP, and it takes some good features from link state routing protocol like OSPF, right? So it's a hybrid technology. It takes the good part from both these routing protocols, and then Cisco developed its own routing protocol called EIGRP. So what does it take from link state? It takes the formation of neighbors. So it forms neighbors, unlike RIP. RIP doesn't form neighbors, it just chatters, right? It just tells its neighbor, whoever the neighbor, it just chatters saying, this is my routing table, this is the route that I know, right? That's what RIP did. But OSPF, before it exchanged updates, it formed neighbors. EIGRP forms neighbors just like OSPF. Also, if you remember RIP did periodic update. Every 30 seconds there was an update, and the update was full routing table. It sent everything it knew to its neighbor. Of course, with split horizon rule, it did not send back route information about the routes that it learned from a certain interface, but other than that, it sends all the interface, all the routes that it knows from its routing table to its neighbor. So EIGRP didn't want to do that. So EIGRP does not do full periodic update. But if you remember, OSPF did hello, so EIGRP also takes that hello concept. So every few seconds it sends hello message to make sure the neighbor is still alive. So RIP did not do that, but OSPF did that, and EIGRP uses it too. What does it take from distance vector? Unlike OSPF, which is a link state routing protocol which learns about the entire network topology before it makes its routing decision, EIGRP does not do that. EIGRP is more like RIP. It just routes by gossip. Now when I say routes by gossip, your neighbor tells you something and EIGRP, just like RIP, would accept it. If the neighbor says that he knows how to go to 10.1.1.2, that's it. He just listens and he does not ask, how do you know, tell me the entire the topology, network topology. It doesn't ask all that. It just believes whatever the neighbor says, just like RIP. So it works like RIP with routing with gossip. EIGRP was a Cisco proprietary routing protocol until 2013. So before 2013, you had to have a Cisco infrastructure if you wanted to use EIGRP. So what happened is, before 2013, even people and companies with Cisco infrastructures, they were reluctant to use EIGRP. In spite of EIGRP being a better protocol, at least my personal opinion, EIGRP is a much better and much more easier protocol, right? In spite of being easier and much better, people were reluctant to use EIGRP and they chose OSPF. And that's why OSPF is the most used routing protocol. That was because they didn't want to lock themselves with Cisco. So if you start your company and if you configure EIGRP, knowing that EIGRP needs Cisco infrastructure, so in future, if you wanted to invest in, let's say, Juniper or some other network infrastructures, right? If you want to expand with other companies' products, you couldn't do it because of EIGRP. So in 2013, Cisco said we would make EIGRP an open standard. That means anybody could use EIGRP if they want. So now if you're using non-Cisco devices, EIGRP is supported. So that's something that happened in 2013, and that is a brilliant move by Cisco. So if you look at little bit of history lessons, RIP version 1 was introduced in 1980s, so early 80s, RIP was introduced. RIP had limitations. RIP had a lot of limitations, especially 16 hop, which was the maximum it could do. Anything more than 16 hop, it wouldn't support. So if the network is a little big, RIP really failed there. So Cisco introduced something called as IGRP, Internal Gateway Routing Protocol, and then it was much better than the RIP protocol. But still, it had more distance vector. It was more related to distance vector than link state. End of the 80s, OSPF, open standard OSPF for IP version 4, which is OSPF version 2, was released with link state. So that was totally different. It was a new concept. Early 90s, Cisco said, okay, this is time. We need to upgrade. We need to enhance IGRP. So Cisco created EIGRP, which is Enhanced IGRP, Enhanced Interior Gateway Routing Protocol. EIGRP suddenly became much better than OSPF because it took few qualities from OSPF, it took few qualities from RIP, and then it suddenly became the best routing protocol that is there. And if you see routing, EIGRP routing, if you in our next video when we look at configurations, you will see EIGRP configuration is much easier than OSPF. So Cisco wanted it to be easy. It wanted it to be converging much faster. It was faster than OSPF as well. And they wanted it to be the best, and it is quite honestly the best routing protocol among the three. Later, RIP wanted to support classless, so RIP did a lot more upgrade, and the RIP version 2 was introduced in the 90s. In the 2000s, RIP OSPF version 3 to support IP version 6. RIP NG also supported IP version 6, and EIGRP v6. These were all three introduced to support IP version 6 because the world was slowly moving towards IP version 6 and all these routing protocols wanted to be ready. So if you remember what we learned in RIP, we realized if, let's say, from router 1, you wanted to go to router 3, if there was some network, The routing table would always use, it would be populated by this route, because immaterial of what speeds this works at. So even if this was working at 64 kbps and these were all 1544 kbps, right? Even this 1544 kbps, RIP would always choose this, because RIP, the only criteria or metric for RIP is hop count, and this has 1 hop count, this would be 2 hop count. But OSPF would look at this whole topology and would choose to go through this. EIGRP also, even though it does a lot like distance vector, it would look at the metric. Now in RIP the metric was hop count. In OSPF the metric was cost, and cost was inversely proportional to the bandwidth. But in EIGRP, it's cost again, all right, the metric is cost, but then it is much more complicated. It takes into consideration bandwidth and delay. By default, these two are taken into consideration, but you could also tune EIGRP to take into consideration load. So if a particular interface is being loaded, you could make sure that you get negative points, and you would prefer something that is less loaded, right? So that's also something that you could do. But for your CCNA level, we will be considering the metric formula, which considers only bandwidth and delay, which is the default formula. Let's try to brush up our knowledge on distance vector, especially RIP. We will see what we learned. So if you remember RIP, when it did, it had distance vector. Now when you say distance vector, like we saw in the previous slide, if there were 3 routers, right, the routing table had 2 information. If let's say it has to go to network 20 whatever 20.0.0.0, so the routing table here had the distance, right? Distance is hop, so this is 1 hop, so distance was 1, and it had a vector. Vector is direction. It had to tell which way to go, whether it has to go this way or that way. So that's why the name distance vector comes. It has a distance, which is in this case hop, and a vector, which is the next route. Where does it have to go? That's vector. That's how the name distance vector comes. So that's how RIP did it. Then it did a periodic full update. So if you remember, RIP every 30 seconds sent out an update. An update, like we discussed earlier, it sends the full routing table. Now, the periodic 30 seconds update of RIP had 2 functions. One was to update its routing table. Whatever is in its routing table is updated to the neighbor. And also 2, it served the function of checking if the neighbor is alive. So if it doesn't get a routing update from a neighbor, 30 seconds if it sends, and it sees that it doesn't get an update from a neighbor or update about a route, it knows that route could be out. So you have the dead timer, hold timer, and all the timer that we discussed. So every 30 seconds it sends and it resets those timers, and that's how it checks for life, checks if those routes or those networks are still valid. So the periodic update, 30 second update, did 2 functions. One update, and then it also checked live. Like we discussed, because of the problem of loop, we use split horizon. So when you say split horizon, what it said it would not send back routes or updates on the same interface through which it learned those routes in the first place. So split horizon rule was used to prevent loop, and route poisoning was another method where there was a triggered update. So whenever a particular network went down, especially if this, let's say in this case, this network goes down, this router sends a poisoned route. Poisoned route means it creates the hop to 16, which is a poisoned route, and it triggers an update. It doesn't wait for that 30-second timer to finish. It triggers an update, it sends it to neighbors saying that this network is now at 16 hops, right? So these are the things what RIP did to prevent loop and how RIP worked. Now, how does EIGRP work? Now, if you remember from OSPF's video, a few videos ago, we did OSPF introduction, and that we learned that OSPF did three things. First thing, it formed neighbors. Second, so that's what EIGRP also is going to do. It forms neighbor, that's first step. Second step is topology exchange, right? So if you remember in that they said LSDB update. No, LSDB exchanges. It exchange LSDB. LSAs, it exchange LSA to update its LSDB. And then third step was to form a routing table. Now, forming neighbor with OSPF was very, very complicated. It had a lot of parameters, and then once it checks all those parameters, it would stay in two-way state. Some of those would go from two-way to full. Some of them would still stay in two-way. In OSPF and EIGRP, there's nothing like that. All it checks 4 parameters. So, like OSPF, EIGRP, once you enable EIGRP, every 10 seconds, it sends out a hello, right? It sends hello. In the hello, there are 4 parameters. There is an authentication. So, if there is any authentication that you set up, there is authentication values. So, both the devices need to have the same authentication parameters. It should both be part of the same autonomous system. So, let's say when you configure EIGRP, you'll see EIGRP and you give an autonomous system. So both the devices should have the same autonomous system numbers. Then it both needs to have the hello message should be coming from the same source IP, right? If there are 2 devices, that there should be a common interface through which, or say a common subnet through which the hello packet is coming, and then the K values should match. Now, K values is, if you remember, maybe I'll show you later, a little while later. In the formula, there are K values, so it's 0 or 1. If it is 0, those whatever the parameter is, obviously it's ignored, and whatever K value that you give as 1, those parameters are used in the formula. So the K value should match, and for CCNA, don't tamper with your K values. Let the K values be the default ones, and that's what Cisco recommends. In fact, don't tamper with your K values. So if these 4 parameters match for EIGRP, you are a neighbor. So those 2 devices will become neighbor, and they would add each other's to their neighbor tables. The next is the topology exchange. So what it does, it sends updates to. It depends. it depends. The hello message would go to this multicast IP address. So this is multicast. Hello will always go to this multicast, and whoever is doing EIGRP, let me just clear the screen. Okay. So hello message will go to this multicast 224.0.0.10, and updates will go to either it could go to the unicast IP address of the neighbor, or it could go to a multicast depending on how it's configured. And these updates are communicated not by UDP or TCP. It uses another protocol called Reliable Transmission Protocol, RTP. It's used by EIGRP. It's a reliable transport protocol, so it can check if the neighbor received the update. So if you send an update and RTP, you can check if the neighbor has received it. If it not, it can retransmit the updates. So it can make sure that the neighbor has seen the updates. Unlike OSPF, you don't have a mechanism for the receiving device to tell that it hasn't received it. EIGRP, now if you remember, we said RIP sends the full topology, full update every 30 seconds. But EIGRP sends full update the first time. So whenever a device comes on, it sends the full update. It sends full information about all the networks routes that it knows. Or when there is a change, if there's a change, it just sends the updates. It doesn't send the entire table again. Whatever that network which is changed, only that network update. So it's more like a partial update. It sends partial updates when required. It doesn't send full update again. So for instance, let's say if you configure EIGRP and for 1 year, nothing changes on your network, all the networks are working, then EIGRP will not send update for 1 year. Unlike OSPF, if you remember OSPF type 1 LSAs, have a timer of 30 minutes. So no matter what happens, even if there's no change, every 30 minutes, the LSA, the type 1 LSA, whichever router generated those LSAs, will see that the timer, which is 30 minutes, has passed, and it will recreate and resend those LSAs. So OSPF, every 30 minutes, LSAs will be updated, and it has to do that recalculation, whatever that does. But in EIGRP, if nothing changes, you will not have anything, no updates, EIGRP updates happening for whatever time that change does not happen. So that's why EIGRP is much more efficient. And the third step, of course, is to build the routing table. So form neighbor, topology exchange, and then build routing table. Now build routing table, we use this metric. This is the formula that is used to calculate costs, and depending on the cost, we create or populate the routing table. Now, what happens? So initially, let's say R1 sends a hello to R2, R2 sends a hello to R1. As soon as this is done, if everything matches, then they will have a neighbor table. So in the neighbor table, R2 will list R1 as a neighbor, and R1 will list neighbor as R2. So R2 is listed in R1's neighbor table, and R1 is listed in R2's neighbor table. Once this is done, it updates. It sends R1 would send the 10.network to R1. So if you see the routing table, it would say 10.1.1.0, next hop is F0/0, and whatever the cost would be shown here. Admin distance for EIGRP is 90. So if you remember, OSPF was 110, EIGRP is 90, and then we would have a feasible distance value. And we will talk about that in a while, but your routing table will have this information. So we talk about metric. So this is the metric. Now, if you see actual metric is slightly more complicated. You will have K value. So you'll have bandwidth, then divided by, you would have K values, then you will have some K values here. This is K3, whatever. I don't know if I have it. Let me just quickly show it to you. So this is from Cisco's website. So if you see, this is the formula K1 and K2 bandwidth, whatever. This is the formula, and these are the default values. K1 and K3 is 1, K2, K3, K4, and K5 are zeros. So if you do substitution of these values, you finally, the formula is reduced to bandwidth plus delay into 256, right? So that's what we have used. So if you look at our, let me just clear this. So we reduce whatever that using the default K values. This is what we get. So we get bandwidth. Now bandwidth is nothing but 10 to the power 7 divided by whatever bandwidth that you have. So we will look at in the next slide, we'll see what I mean by the least bandwidth, but the formula is always 10 to the power 7 divided by least bandwidth plus cumulative delay. Now cumulative delay is the delay from that whichever router we're talking about till the subnet that we're talking about, where we are trying to find the route. So the delays, you need to add all the delays in between, right? And least bandwidth is the lowest bandwidth between all these things. So we will see how that is derived. But this is the formula. Just remember this formula. Talking of EIGRP, these are the 4 topics that we need to learn. That's feasible distance, reported distance, successor, and feasible successor. So let's take a topology and we'll try to understand these 4 terms. And once you understand these 4 terms, I think we are ready to start configuring EIGRP. So let's assume we are trying to populate R1's routing table. R1's routing table is what we are interested in, and we are trying to go to this network 10.1.1.0/24, right? Now, this is the bandwidth and delay. Now, bandwidth and delay you could have by default. So by default, gigabit is 1 gigabit per second, GBps. You have to convert that into kbps. That becomes 1 million kbps, right? 10 to the power 6. Or you talk about 100 mbps, that's 100,000 kbps. If you're talking about Ethernet, that's 10,000 kbps or 10 mbps. You talk about serial connections, 1544 kbps. So accordingly, the delay also is calculated by Cisco. So if you go to show interface G0/0, it would tell the whatever that bandwidth is and whatever delay is, right? These are the physical properties. So for instance, if you look at serial bandwidth by default is 1544. Even if this is a 64 kbps line, it would still say 1544 kbps. So you as an administrator should be very careful, and you should make sure that you put the correct values for the bandwidth. And of course, delay would be, you could again change the delay with the command. So if you go into that interface and say bandwidth, then you can give bandwidth, and delay, and you can give delay. So whatever that you want, you could give from that interface. But whatever that is configured, you need to make sure that, especially in serial, if you leave gigabit Ethernet and fast Ethernet, if you leave the default values, you should not have much problem. But your serial interfaces, be careful that you have to set whatever the LAN speed is. Another thing that you need to look at, and these are all saying milliseconds, ms is millisecond, but actually they're all microseconds. Micro is a sign like that, mu, if you know what mu is. So microsecond, but I didn't have this sign mu s, that's why I said ms. So if you look at Cisco, it says us. Us is nothing but u, they're writing u for microsecond. So it's actually 100 microseconds, 10 microseconds. Another thing what you need to be careful is, if you look at the show interface G0/0, it lists the delay by microsecond. But if you're configuring, if you go into the interface and then you want to configure a certain delay, you say delay. If you look at the unit there, it says tens of microseconds. So 10 microsecond will become 1/10 of microsecond. So we will look at that tomorrow in the next video, that is, when we do configuration. But this is something you need to be careful. The configuration, when you configure manually, it is not micro, it is tens of microseconds, so it's less. So let's do this. And it's not only for configuration, even in our calculation, it uses tens of micro. So if it's a 100 microsecond, in the formula for delay, it is actually taking 10 because it's doing tens of microsecond, right? So you need to remember that, right? So when you do the calculation. So now this is the bandwidth for this interface, and this is the delay. This is the bandwidth for this interface, and this is the bandwidth for this interface, bandwidth and delay rather, bandwidth and delay for this interface, bandwidth and delay for this interface, bandwidth and delay for this interface, and this interface. So we need to first find feasible distance. Feasible distance is the metric, right? It's a metric. Once you put the formula, you put all that calculation, whatever that you get is the feasible distance. So for this, if you use the formula, that would be 10 to the power 7 divided by, this is what, 10 to the power 6, 10 to the power 6. So if you do 10 to the power 7 divided by 10 to the power 6, that is 10, right? If you know what it is, 10 to the power 7 divided by 10 to the power 6 is 10, plus delay is 1 microsecond. If you do tens of microsecond, that is 1. So that is into, so if you remember formula, this into 256, that is 11 into 256, which is nothing but 2816. That's the value of your feasible distance, and this is the value. So if you look at the cost, for this router 5 to go to 10.this network, that's directly connected, but the feasible distance is 2816. Now this 2816, when EIGRP sends routing updates, it would send this information saying the bandwidth is so and so, the delay is so and so. Now, whatever that value to feasible distance would be considered, no, so that's feasible distance. So whatever that router 5 is sending to router 2, the feasible distance of router 5 will become the reported distance for router 2. So router 2's reported distance is router 5's feasible distance. So feasible distance is being reported, so that becomes reported distance. So all these devices' reported distance is the feasible distance for this device, right? Now we need feasible distance and reported distance for a reason. You'll see that. So that's what reported distance. Reported distance is the distance, feasible distance of the next device which it's reporting to you. Now when router 2 makes the calculation, what did it do? It did the same thing. So let's do this again. When router 2 is doing it, now router 2 needs to look at the bandwidth. Now between this and this, it was reported 1 million kbps and 100,000 kbps, which is the lowest bandwidth. So if you remember the formula, it says the lowest bandwidth. 100,000 is lowest bandwidth. 100,000 is nothing but 10 to the power 5. So it's 10 to the power 7 divided by 10 to the power 5, which is nothing but 10 to the power 2, which is 100, plus what is the cumulative delay? 100 plus 10, 110. 110 tens of micro is 11. So 100 plus 11 is equal to 111 into 256. Whatever you get is this value, 28,416, which is the feasible distance for router 2. Same way here. Now we're talking about 10 to the power 4, that is 1000. If you divide this bandwidth part, you'll get 1000. And cumulative delay is 1010 milliseconds, microseconds rather. 1010 is 101 tens of microseconds. So 101 plus 1000 is 1101 into 256. You would get this value, 281,856. Similarly for this, because in this case the lowest bandwidth is the same, because this is 1 million, whatever, 1 gigabit Ethernet. So it gets a FD of 3072. Now this 3072 goes to the next device as the reported distance. This will go as the reported distance, and this would go as the reported distance. Again, it would use the formula. So now when it comes here, this bandwidth is gigabit Ethernet again, but the reporting bandwidth is 100,000, which is lesser, 100,000. So it's using the formula. Now let's do this here. I'll clear this again. Now when router 1 is doing the calculation, it's getting a reported bandwidth of 100,000. Its bandwidth is 1 gigabit. Because 100,000 is less, it is going to use 100,000, which is 10 to the power 5, 10 to the power 7, which is nothing but 100. Cumulative delay 10, 100, 120. 120 is nothing but 12. 112 into 256 is 30,976. That is the feasible distance. Similarly, the feasible distance is 284,416. Again, it is reporting 10,000 and 100,000. So it will use 10,000 in the calculation, and it will add all the delay until the end. So what happens when EIGRP sends the updates? It sends 1010 microsecond, because that's what is in the update. But this is particular only to this interface, right? So then this device will definitely know whatever the delay it is sending, plus it would add its own delay, would get the cumulative delay. So after that, it does the feasible distance, which is 284,416, and this device gets 2,170,360, right? Now, all three devices have a feasible distance. Depending on the lowest feasible distance, so router 1 has 3 routes to go to this network, okay? So it looks at the least feasible distance. The least feasible distance is definitely 330,976. So this route becomes the successor, right? The lowest feasible distance becomes the successor. And it also, in the routing table, there's something called feasible successor. That means in case this route ever fails, there should be somebody for immediate backup. So that backup is instantaneous. So To make somebody a feasible successor, there is one rule. The rule is the reported distance of the other, like in this case, the other two routes, the reported distance should be less than the feasible distance. So reported distance is 281,000, which is not less than this feasible distance. So this will not become a feasible successor. The reported distance is 3072. So definitely this can become a feasible successor. So this will go into the routing table as a feasible successor. That means when this network ever goes down, traffic will start going through this, right? That's feasible successor. And that's why, and this changeover, this switchover, so whenever a network goes down, the routing, the time it takes for the routing table to get an alternative path is known as the convergence time. RIP is very, very slow. It takes a very long time to converge. OSPF, few seconds. EIGRP is instantaneous, and that's why EIGRP is so beautiful. It's very efficient because instantaneously it switch over because there is already a feasible successor in its routing table. Now what happens if both of these, like the successor and the feasible successor fails? When that happens, EIGRP will run an algorithm called as dual, D-U-A-L. What it does is, because now it knows, when it does the calculation, it knew that there is a third route. So what it does is it sends a request, and that device will say, yes, that particular route is available. So it sends a reply, right? This is dual. So it sends a dual request. Once it confirms that, it will take this, whatever route is available, it would put that in the routing table, and that takes about few seconds to do it. So even if your feasible distance fail, or feasible successor fails, EIGRP converges quite fast. I mean, maybe few seconds, 3 seconds, 4 seconds, 5 seconds, 10 seconds, whatever the time it takes for this other neighbor, whichever neighbor that is active, the active neighbor to reply. As soon as the active neighbor replies, it puts that interface, or rather that route, on the routing table, and we are back doing business as usual. So these are the 4 critical terms in EIGRP: feasible distance, reported distance, successor, and feasible successors. And I hope this made sense. If not, watch it again. I'm sure it would make sense how these successors and feasible successors are found. Thank you so much for watching. We will be back very soon with the configuration part for EIGRP. Thank you, and see you all back very, very soon. Bye-bye.